In 1997, Brazilian fullback Roberto Carlos shocked the world with an apparent miracle goal that seemed to defy physics. The ball was hit from 35 meters out, and it looked like the ball changed direction through its flight. But if we truly analyze the forces that were acting on the ball that day, we can come to appreciate the physics behind a perfect soccer kick. This image was created by English physicists in 2010, and it shows the path the ball would take if gravity had no effect. The spiral path that the ball follows is generated by the spin applied during the contact with the ball. This is known as the Magnus Effect. Such as in this video, the Magnus Effect makes it possible to curve a ball around a goalpost from a point that is directly in line with the post. As I'm sure you are wondering, what exactly is the Magnus Effect? Well, it is a force that was first described by German physicist Heinrich Gustav Magnus in 1852. And he described the effect as a force that acts perpendicular to an object's velocity. The force takes effect when an object is spinning on an axis and traveling through a fluid. Bernoulli's principle states that the speed of a fluid is inversely proportional to its pressure, so in effect, the faster that an air is traveling, the less fluid pressure it exerts. So now imagine a ball is spinning through the air. The airflow is going in the opposite direction of the object's velocity, and it is spinning clockwise from a bird's eye view. The airflow on the right hemisphere is being sped up by the ball, as the spin is acting in the same direction. However, on the left hemisphere, the ball's rotation is slowing down the airflow. Bernoulli's principle shows that there will be a decrease in air pressure to the right of the ball, and because objects will tend to want to balance pressure, the ball will experience a Magnus Force that will pull it to the right. The Magnus Force might be one of the biggest factors in a perfected kick, but the speed of the ball also matters. In order to get the ball past the goalkeeper, it must be traveling with sufficient speed. Most professional players kick the ball with a foot velocity of around 30 meters per second. That is quite fast. However, the ball will not carry the same speed, as there is always going to be lost energy. This is where the coefficient of restitution comes in. The coefficient is a unitless value that shows the conservation of energy through a collision. In a perfectly elastic collision, where the object retains all the energy of the initial contact, the coefficient will have a value of 1. However, in the real world, that is not achievable. To find the value of the coefficient, a Fifa test can be performed. Drop a ball from a recorded height onto a rigid surface and find the height of the subsequent bounce. Then, you take the gravitational potential energy at the bounce height and divide it by the gravitational potential energy at the drop height. After doing this, you square root the value. That gives you the coefficient of restitution, represented by E. After finding out the speed at which the ball is traveling, you need to factor in air resistance. In the real world, air resistance is a huge factor. Depending on the shape, size, and material of the object, drag will have an impact on the final speed at which the ball is traveling. One important idea to note is that the air resistance force will change depending on the speed at which the ball is traveling. Represented by this formula, the force on the ball will decrease as time goes on. This is because the acceleration experienced by the ball is slowing it down, and so the value for velocity is decreasing. This is exactly why an object reaches terminal velocity during freefall. As the object accelerates due to gravity, its velocity increases, and the resulting drag force will increase to the point where the force balances the gravitational force, and there is no more acceleration towards the ground. In my experiments, and to model it simply, without using instantaneous rate of change and complicated mathematical models, I will assume the value for velocity to be the exact value of the ball after contact with my foot. As for the coefficient of drag, I will assume that the standard value of 0.47 for a sphere applies to the ball. So after all is said and done, I can use this knowledge to find out the exact stats of my free kick. Here is a clip of the entire kick. Here are some videos of recorded constants during my kick. First, I found the mass of the ball to be 0.438 kilograms. Then, using the FIFA test for restitution, I found the coefficient of restitution to be 0.829, again using the formula. This about lines up with the average for a soccer ball, which is 0.8. So after all this pre-testing, I put on my cleats and started to measure the field. The next thing to do was pick a spot to kick from. I chose a spot that was directly in line with the center of goal, and I measured it to be 72 inches from the 18-yard box, meaning it was 20 yards out from the goal. Doing a quick conversion, this leaves the spot to be 18.288 meters from the goal. Next, I had to practice kicking the ball. I I kicked multiple times along a half-meter long stretch and found a kick speed that was repeatable and accurate. I slowed down the clip frame by frame and did some conversions to see that my foot was moving at a speed of about 15.4 meters per second. After doing this, I had practiced hitting the ball at the same speed. This time I would spin the ball. The technique for spinning the ball is to wrap your foot around the ball just as you make contact. The goal with this clip is to find the angular speed that the ball has, or in other words, how fast it rotates. I picked a spot on the ball and marked it with Sharpie. Again, I went frame by frame and found the angular speed to be 6.06 rotations per second. It's now time to put it all together. I used a protractor to measure a line that was 15 degrees from perpendicular to the goal line, and I hit the ball along this line. I also used the clip to determine what angle the ball initially traveled in terms of height, which was 18 degrees. This next part is a little confusing. If we imagine that we were looking at the kick from above, as seen in this image, we can determine the horizontal location of the ball. Using Magnus Force as the acceleration, and we know what the initial speeds and the distance are, we can use kinematics to find out the horizontal location of the ball. By first multiplying the velocity of the foot by the coefficient of restitution, we get the ball velocity. Then we must multiply that by the sine of 15 degrees to find the velocity component that lies on the same axis as acceleration. Then we use the horizontal displacement to find the time the ball was in the air for, which is about 1.483 seconds. We must then analyze the Magnus Force. The Magnus Force is quite complicated. The cross product between the axis of rotation's angular velocity and the object's flight velocity. After multiplying these two values and using the right-hand rule, we then multiply it by the air resistance coefficient, which we valued as 0.47. After doing this cross product, we get that the Magnus Force is 1.49 newtons. If we then divide this value by the mass of the ball, according to Newton's second law, we get negative 3.41 meters per second squared as the acceleration. After doing kinematics, we get the value of displacement from the center of the goal to be 2.14 meters to the right. Now to do the same thing to find the displacement above ground. We hit the ball up at an angle of 18 degrees, and our initial velocity is the same. We know that gravitational acceleration is negative 9.81 meters per second squared, and we know that the ball is in the air for 1.483 seconds. Doing kinematics, I determined that the ball ended up 1.84 meters above the ground. To determine the final velocity of the ball, we must factor in air resistance. 1/2 times the cross-sectional area times the density of air times the coefficient of drag times the velocity squared is the air resistance force. And then if we divide that value by the mass of the ball, we get the acceleration due to air drag. In this case, it mainly acts in the direction of horizontal velocity. So using constants of air density and the value of cross-sectional area, I got the value of acceleration due to air resistance to be negative 1.67 meters per second squared. After doing the calculations, I found the final speed of the ball to be 9.5 meters per second. So in all, my soccer kick ended up hitting the net 2.14 meters to the right of center, at a height of 1.84 meters, and at a final velocity of 9.50 meters per second.